So yesterday during the lecture, we talked about this lab very briefly, but by skimming through everything, I can tell there might be some minor points that you need to understand. So first, you are defining the width and length, right? So you can see, I believe this is a control I, right? You select it and control I. You can select the width and length. And there's the bigger ones, the smaller one. Usually the bigger one is the width and smaller is the length. So what's the unit for that? I mentioned this once or twice, I think, in the class last week. It's actually lambda. So lambda is 300 nanometers. And you can see why the minimum length. You can change the width, whatever you want, okay? But there's a minimum. Minimum is 2. So 2 means 2 lambda. Because 1 lambda is 300 nanometers, so 2 lambda becomes 600 nanometers. It's called the lambda rule. So all these parameters are in lambda. The reason for that is, remember this is the 500 nanometer technology, so the minimum length of the transistor is going to be 500 nanometers. And then we define the 2 lambda, which is 600 nanometers, is a little bit larger than the minimum to improve the yield. So it's make sure everything will be functioning. Okay, that's first thing you need to know. And then the SPICE model, you got to change it. Make sure you change it to NMOS and PMOS. If it's the NMOS, you change it to NMOS capitalized, because in the model file, there will be a model file like this, C5 models.txt file. Okay, I don't have a link. I probably will. I'm gonna upload the link to this website so you can download it. Right. So this model file has to be. You have to place it inside the folder directory, which has all the design files. If you look at your electrical VLSI, you have all the libraries you build, right? All the like CE338 and all these other files. So this one needs to be directly in that directory. You don't want to change it to anywhere else. Okay? So it is able to, whenever it runs the SPICE code, let me show you the code. See here, it's dot include. So this is where you include the model file. Dot include. I mean, I placed under the C drive, but if you have it in the same directory as your design file, you don't have to have a path in front of it. Just directly C5 models.txt. Okay. Other issues I saw in the past is that in the path over here, you have a space of the folder names and the weird symbols within it, which may cause issues. So make sure that there's no space of any of the names in the folder, okay, in the path. Okay, and so whenever we are using transistors, we do need a model file. But for the NWEL, like last time we simulated the NWEL resistors, it doesn't really need a model file, because the model files really defines NMOS and PMOS transistors. The parameters over there, including the mobility of the electrons, the thickness of the oxide, and a bunch of other materials. So you can double click and open it up. You can look into the details of the parameters. And so I talked about this briefly yesterday regarding the force terminal. Okay, if you bring this up, you can, short. If the PMOS, you short it to the highest potential of the circuit. If this is the NMOS, you short this force terminal to the lowest potential of the circuit. That's the only difference. If you don't have this force terminal displayed, like the ones here, right, which is also fine. We are just treating this one by default. The body is always connected to the NWEL, because the PMOS is being put in the NWEL. So the NWEL is the body of the PMOS. The P sub is the body of the NMOS. Remember? Because we fabricate PMOSes in NWEL. So NWEL is the body of the PMOS. And we fabricate NMOS directly in the P sub. So the P sub is the body of the NMOS. And we need it's called a well tap or body tap. So these are the, because PMOS is in the NWEL, that is why we need the N plus as the N tap, right? And P plus is the P tap for the NMOS. Like tongue twister. But you got that, right? You got the idea? Okay. So this one by default we didn't display it, but actually it's a N plus or P plus. N plus, right? So it's the PMOS, we need the N tap, so the N plus is being directly shorted to the highest potential of the circuit. VDD, okay? You display it, you have to manually short it to VDD. That's the only difference. All right, so this is NMOS, the PMOS and NMOS. This is the NMOS, right? You drag it and you place it in here, and they already draw that poly, the gate in the middle, and these are the green colors are the diffusion. And keep in mind, the channel length is defined by the width of the poly, which is over here. So in that case, it doesn't really matter how far away this is from the poly. You know what I mean? These are just the diffusion. If this is NMOS, these are just the N plus. And we can see this node is a bit different because, you know, it's going to be challenging that you do everything manually by yourself. But all these things are repeatable. You are just repeatedly using them. So that is why the library directly put a diffusion and via and metal one on the top of each other. Okay, and all these slashes, the slashes over here, represents a P well. It's a P sub. It's really interesting. It's a P sub, even though it's just a substrate, but it's just showing that this is you can call it P sub or you can call it P well. But it's basically not a well, it's just a P substrate, it's the body of the wafer, it's the whole wafer, right? So the NMOS, you can see the N plus is directly put in the P sub, and then you need a via and metal one, right? So that's this little node over here. And you place one here, and then you start moving them close to this transistor with the gate and diffusion node over here. And you place the little poly, which is a gate connector. You can see the color is changing because it has an overlay of metal one on the top. So it's basically the light blue color on the top of the poly. So it shows this little grayish color. So you have this one, you can directly, it's the connector to the poly, and you make everything ready, then you start moving things next to each other. So what is this guy? Because this is the NMOS, right? NMOS. So for NMOS, we need a body tab. So this is the body tab. It's going to be P plus. P plus. So we have everything ready. 4 terminals. Remember, the transistor has 4 terminals. 1, 2, 3, 4. And then you start moving things close to each other. But before that, you change the width. You right-click and change the properties. The transistor got changed a little bit. And then you move your poly to metal one node to this location. You don't want to move it too close, because if it's too close, it's this poly layer here is too close to diffusion. It's probably reporting DRC errors. So you want to keep a certain distance, but how close? So you'll find out. So the way to do that is you can either left click and drag, and whenever it's getting very close to all the other components, it's going to show an error text in the tool. If you don't see the error, which means you can still move it closer and closer, but until you see the error, you move it one step back. So another way to do that is usually how I do it, which is you left click, and you can use the arrow buttons on the keyboard to move it up and down, left and right. So you can, for example, you place this guy here, and you single click, left click, and then you start pushing that right arrow, you keep pressing it, so it's actually moving step by step on the grid. All right, until you see an error pops up, you move it one step back. Perfect. That will be the smallest distance you can use. It's saving a lot of space. So it's rather than place it pretty far away from where you want to get rid of all the DRC errors, let's just move it using the push buttons, right? Move it step by step until you see that error. Same for all these nodes as well. You can see that we are changing the width. Whenever this is getting a little bit wider, you can fit 2 vias in here, and the tool directly adds these 2 vias to it, because more vias will increase the reliability of the node. You know, if that via is not working, disconnected, you still have a backup via. So that's why whenever you have more space in there, the tool will directly or automatically add more vias to it to increase the yield. So you got this one, you make it longer, and then you got more vias, you know, automatically, and then you have start. So I think everything's ready. You can start moving things close to each other. Either way, you could either left click and right click to connect the diffusion, or you can make it closer and then make the connection. It doesn't really matter. After you make the connection with the green area, you can still left click and keep pressing the button to move it closer. Eventually, it looks like this. So why I know that I need to stop right here, because if you keep pressing one more time, it's gonna show an error. That's why I pressed it one more step back after I saw the error. And this is probably the ideal or the optimized distance. Is not too big and no DRC errors. And you can see, even though the green color here is the NX, right? It's all N plus, but the N channel, the Nmost channel, is really just defined by the poly. Remember why is that? Because we place the poly on the top first, then it deposit all the N plus material, so the poly will prevent N plus from getting into the wafer, and that's why you are getting a gap underneath the poly, and that's the length, the channel length, but not all the rest. Since you can see for the rest of the N plus over here, it looks like the green area is huge. I mean, these are all N plus, but it doesn't matter. I mean, these N plus over here, it won't get underneath this poly because this is blocking the N plus from getting to the wafer. And you can see this area is showing a different color. Why is that? Why does this area looks different? It should be crystal clear, right? There's no magic. There are just a certain number of layers. There's no magic. There it is. So remember, this is N plus, and the node already fabricated. You can see this node before I move it here. The same thing. So the node over here from the library is already defines this N plus, right? And this metal one, which is the light blue color, but on the top of the green shows a different color. That's the metal one. And these are the two vias. So this component already has N plus, via, and metal one. That's everything on the top of each other. So that's all the layers for this component. Same thing, make the connection and start dragging and moving things back. Yeah, even though it looks ugly at the very beginning, but if you use the arrow, you select it and use the arrow button, you can move it back. So it eventually looks like this. And then you start moving this component back until you see the error. Then you'll stop over there. See? You can see this. And remember, this is Nmost, so Nmost need a well tap to avoid body effect. So the Nmost is well tap is a P plus, and this guy has a P plus in there, and metal one and vias. So I have to move this node close to this one and make sure this slashed area is really interesting because there's no physical connection, but you still have to understand what's really going on from the cross-sectional view. So if you look at this one, it has all the slashes. It's the slashes at the same pattern, which means they're the same layer. Okay, so these slashes, if you want to have this P plus being placed in the same well as this Nmost, how can I do that? I mean, for Nmost, everything has to be put in the same wafer. But still, you just still have to understand, if you want to put this P plus in the same well as this Nmost, so they are in the same well, right? I mean, for Nmost, there's no difference. They are in the same wafer. But in PMOS, I'm going to show you really quick. But for this one, if you want to place this one in the same well, which is the P sub, as this one, you have to move this and have all this slashed area overlap with this one, or at least making a contact. So you can guarantee that they are in the same well. It's just a concept, but for Nmost, there's no way that I'll put the P plus on a different wafer and you're making the same chip. They're always in the same P sub, right? But for the PMOS, it will be different. Let me draw a picture for you guys. So for example, we have here's a wafer P sub, right? And I'm having a PMOS. As we know, PMOSes are being fabricated in wells. All right, so I grabbed the PMOS from the library. It's in the N well, no problem. And then I need a N plus, okay? Just a pure N plus node. So why do we have N plus? To avoid body effect. And the N plus should be an N tap. N tap is tapping that N well, right? So making a connection. And I need to short that N plus to VDD to avoid body effect. However, is this guy, you know, if I do this, because that's an N plus or N node, N tap, right? From the available from the library. So that's a component I can grab from the library, and that's a PMOS I can grab from the library. If I place them, there's no overlap in between or not having contact. What's the problem with that? The N tap is not helping. Is N tap helping? No, they are not even the same N well. So how to do that for the layout? Right? You have to move it close. If you are doing the layout from the top, right? From the top, you got the N plus, which is the well tap. You got a PMOS. You have to move them close to each other and making contact at least. Or overlap is also fine. They are still in the same N well, but make a contact at least. So what you want to do here is, if you look at the examples, let's look at the P. You know, this is NMOS, but let's take a look at the PMOS example as a PMOS. You see here, right? So that's the N tap, N well tap. You have to move it close to each other. These are the dots are an N well layer, and they are overlapping. Okay, that's a key point. For simulations and the SPICE code, I'm not seeing a problem over here. And that's it. It's just the two different transistors and two IV curves. I'm gonna send you guys a C5 model file to announcement, but also upload a link to the tutorial as well. All right, any questions by far? No? All right, you can get started.